So now we have the second lecture on the series of talks arranged by CMSA in Harvard, jointly with Tsinghua University, the Math Center there. And this is a series talk on history and literature in math science. And it will cover many different disciplines. And today, right now, Simon Donaldson will cover in the subject of Yang-Mills theory, which is important in both geometry and topology. And Simon has been the master of this subject in the last 40 years, since the first time I met him in Princeton. He was a rising star at that time, but now he is a master of this subject in low dimensional topology, geometry, and high dimensional instanton construction, and all this has been leading us for such a long time. And I'm very happy that he is willing to give this talk on the history of ADHM construction of Yang-Mills instanton. Okay, Simon.
Oh, hello, everybody. Thank you to Professor Yao for the invitation to give this talk and for the introduction. And thank you all for coming to join this online lecture. The topic I've chosen focuses on work from more than 40 years ago of Atiyah, Drinfeld, Hitchin, and Manin. But I'll begin by setting some of the background for that work, and then later in the talk I will discuss some developments after their work. So let's begin. I want to describe the problem which they solved. So I'm sure a lot of this will be extremely well known to many of you, so apologies to those people. Let's just recall in electromagnetism, we working on space-time, on Minkowski space, we can put the electric and magnetic fields together into a skew symmetric tensor, Fij, and this can be represented in terms of a potential. So according to the expression given. So again, going back to the individual electric and magnetic description, the potential A will be made up of the familiar electrostatic potential and the magnetic potential vector field. But in the four-dimensional picture, this this skew symmetric tensor is a two-form. Then the Maxwell equations, the equations of electromagnetism, are generated as the Euler-Lagrange equations of a functional. In the case of
Simon, are you showing some slides? It's not moving. It's still the first page.
It looks like you're still on the first page.
Oh, I'm seeing the second page. So maybe.
We don't see it.
No.
Do you want to try stopping your share and
I'll stop the share
again?
and then do it again. Let's try that.
Okay, good.
There we go.
So we're seeing the formula for Fij expressed in terms of the derivatives of the potential AI. Is that, can everyone see?
Yeah.
That? And then the functional which generates the Maxwell equations is just the essentially the L2 norm, or the indefinite analog of that. We call it E. So in 1954, Yang and Mills, studying more sophisticated particle physics, considered the possibility of letting the AI take values in the Lie algebra of a Lie group. So for our purposes, we will usually take this group to be the unitary group, which is a compact group. But sometimes we'll want to consider the full complex group of all complex matrices. Anyway, the key thing is that they added a nonlinear term to the formula involving the bracket in the Lie algebra between the components of the potential. You could define a functional as before, a Yang-Mills functional, and this generates Euler-Lagrange equations, the Yang-Mills equations. Some years later, it was realized that this formula with the nonlinear term is exactly a very familiar formula in differential geometry for the curvature of a connection. So from this point of view, the A's represent a connection on a bundle with structure group G. So we'll actually talk about a vector bundle will be the most convenient formulation. And then the F is just the curvature of this connection, very familiar in differential geometry. Well, these developments, both of the notion of a connection and curvature, and also the link to particle physics through the Yang-Mills equations, was discussed in the lecture of Professor Yao in this series. In any case, I don't want to go into review the whole theory of connections, but let's just recall that if we think about the covariant derivative of operator defined by the A's, so we just take the ordinary derivative, d by dxi, and add on a zeroth order term given by multiplication by the matrix AI, then the curvature appears as the commutator of these covariant derivatives in different coordinate directions. So going to the next slide, not a very professional picture, I'm afraid. The idea is that if we, for example, going back to electromagnetism, we talk about the wave function in quantum mechanics, but really that shouldn't be thought of as a function, but a section of a vector bundle. And we should replace the ordinary derivatives by these covariant derivatives involving the contributions from the electromagnetic potential. This is the way we should modify the usual quantum theory in the presence of an electromagnetic field. So all of that discussion was in Minkowski space-time, with an indefinite signature, but we're going to work on Euclidean four-dimensional space, R4. So if we now look at the space of two forms, as before, the thing, then a special feature of four dimensions is that these split into the sum of the self-dual forms, lambda 2 plus, and the anti-self-dual forms, lambda 2 minus, as corresponding to the eigenspaces of the star operator. Just to remind you, for example, if we take the star of dx1, dx2, that means we take the complementary indices, we get dx3, dx4. So dx1, dx2 plus dx3, dx4 would be an example of a self-dual 2 form. Of course, we can do the same in any, we can do the same in higher dimensions. We will get a splitting of the forms in the middle dimension in a similar fashion. The special feature of dimension 4 is the splitting occurs for two forms which have a particular significance in terms of differential geometry through the notion of curvature. In any case, in our situation then, the curvature we can write as a sum of self-dual and anti-self-dual components, F plus plus F minus. And our Yang-Mills functional is just the sum of the squares of the norms of those two things. On the other hand, if you take the difference of the norms of those things, then you find that this functional is, in a sense, trivial with respect to to compactly supported variations. If you take a compactly supported variation in your data, then you can write the variation of the integrand as the derivative of something, and so the integral is 0. So it follows just from that, without going into detailed formula, that if you have a connection with f plus is 0, then that is a solution of the Yang-Mills equations. It's a critical point of the functional E, a solution of the Euler-Lagrange equations defined by the functional E. So these are the central topic. These connections are called anti-self-dual Yang-Mills instantons. They're special solutions of the Yang-Mills equations, which occur in the case of dimension 4. So just to be clear, these things are the solutions of a nonlinear partial differential equation for our connection, represented by the data A, because the formula for f plus involves that quadratic term with the bracket of involving the bracket in the Lie algebra. So the study of these things is studying a nonlinear PDE. So at the beginning we talked about putting the electric and magnetic fields together to get this object F, just to see in a different way what the meaning of this anti-self-dual condition is. If we went back to choosing a space and time description of our four-dimensional space, but now in a Euclidean version, then we would represent our curvature in terms of electric and magnetic components, and the condition is just that the electric field is minus the magnetic field. If you take the ordinary Maxwell equations, then they are symmetric between electricity and magnetism up to some signs. When we go to the Euclidean version, then the signs change around and we get a perfect symmetry between electricity and magnetism. And these anti-self-dual instantons are the ones which are symmetric in that sense. We can also take E equals plus B, but that would just correspond to a change in orientation conventions. It would make no real difference to the discussion. So these equations, they are conformally invariant. They actually only use the metric structure on R4 up to a scale. So everything extends to the compactification of R4, given by adding a point at infinity to get the force sphere. That's the standard round Riemannian metric on the force sphere is conformally equivalent to R4. Now, according to a famous analysis result of Uhlenbeck in 1979, studying solutions on the force sphere is the same as studying solutions on R4 with natural decay behavior at infinity. In fact, the same as imposing that the energy, E, is finite. So we can pass interchangeably from working on the compact manifold, the force sphere, or working on R4 with suitable growth conditions at infinity. And from this point of view, on the force sphere, then the functional we call kappa, we wrote down before, is a very well-known thing. It gives a characteristic class of the bundle we're working with over the force sphere. So in the case of the unitary group, then up to a factor of 8 pi squared, kappa would just correspond to what's called the second Chern class of our bundle, a topological invariant of the situation. So that sets up the background to describe the problem solved by ADHM. the problem is to describe all of these anti-self-dual Yang-Mills instantons over the four-sphere for, well, let's say for the compact classical groups. That's to say, for the unitary group, is what we'll talk about, but the same techniques apply to the other classical groups, the symplectic and orthogonal groups. So this is the problem, I say, was solved by Atiyah, Hitchin, Drinfeld and Manin sometime in 1977. And you can read a bit about the story of that in Atiyah's commentary on volume 5 of his collected works, written in 1986. So, with the help of Nigel Hitchin, I finally saw how Horrocks' method gave a very satisfactory and explicit solution to the problem. I remember our final discussion one morning when we'd just seen how to fit together the last pieces of the puzzle. We broke off for lunch feeling very pleased with ourselves. On our return, I found a letter from Manin outlining essentially the same solution to the problem and saying, "No doubt you've already realized this." We replied at once and proposed that we should submit a short note from the four of us. So that was the story of the solution of these problems essentially by independent groups, Atiyah, Hitchin and Drinfeld and Manin. But one of the attractive features of their solution is that while it goes through sort of sophisticated mathematics of different kinds, the actual answer can be expressed rather simply. So let's, without more ado, outline what the answer is. We'll work on R4, standard coordinates, xi. So we're going to consider a family of linear maps depending in a linear fashion on the coordinate x. So these are going to be linear maps, lambda x, from C2k plus r, the complex vector space of dimension 2k plus r, to C2k. So having the form specified. So everything is determined by 5 2k by 2k plus r matrices, Li and m, I going from 1 to 4, or 0 to 3. So we want to assume that these maps are surjective for all x, and then there are going to be some other conditions which we'll come to later, but some very algebraic conditions on these matrices. Then the construction goes as follows. We take, at each point x, we take the kernel of lambda x. Because lambda x is surjective, this is an r-dimensional vector space, and as x moves over R4, it defines a bundle, a rank R vector bundle over R4. And the statement is that the induced connection on that bundle is one of the anti-self-dual instantons that we're after. The second shown class, the topological invariant, is the number k, and all the instantons with rank R, the UR instantons with second shown class k, arise in this way. So our nonlinear partial differential equation is solved in terms of very finite dimensional data, a collection of matrices satisfying some algebraic equations. And towards the end of the talk, we will come to write these equations in a more explicit fashion. But let's just say, what do we mean by the induced connection? So this is just the same construction as appears in elementary and classical differential geometry when you're discussing the tangent bundle of a submanifold in Euclidean space. That's to say, we define a connection by using orthogonal projection. So to say that more formally, our bundle, we're calling it E tilde, it's on the one hand a sub-bundle of the trivial bundle with rank 2k plus r. I'm using an underline to denote a trivial bundle corresponding to the given vector space. But even also we have orthogonal projection, which defines a map pi from the bigger bundle to E tilde. So we have an inclusion map iota and a projection map pi. So now to define our connection or covariant derivative on the sections of E tilde, we first apply iota. We can consider them as sections of the bigger bundle. But there this is just a trivial bundle, so we have a standard flat connection, just ordinary differentiation. That will take us outside the subbundle, but then we project to get back to the subbundle E tilde. So this is, as it's just exactly the same way that you define the derivative of vector fields on a submanifold in classical differential geometry. Very, very simple construction. So why do I choose to talk about this, this work? What is the special significance of it? Well, there are many things that one could say. On the one hand, it was one of the first applications of sophisticated techniques from modern differential geometry and algebraic geometry to a problem of great interest in physics. On the other hand, it's also a beautiful piece of mathematics which can be approached from many directions and connected with many other things, as perhaps we'll see some of later in the talk. What are the references? The note that Atiyah referred to, that appeared as in 1978, Physics Letters, the 4-author note, just 2.5 pages. A greatly extended sort of exposition was written by Atiyah soon after, a write-up of the Fermi lectures in Pisa. This is a booklet of close to 100 pages, and so this came out, say, in 1979. I started as a graduate student in 1980, and so this was an important part of my education, this booklet. You can learn a lot about the geometry, not just of this problem, but of all kinds of ideas from geometry from this booklet. So I greatly recommend it to anyone. Well, as I mentioned, there are many points of view that we can take on this ADHM result, the ADHM construction. But for the main part of this talk, I'm going to follow pretty much the point of view that they took. I follow, and this goes through something which is of independent interest. It's called the Penrose Twistor theory. So this Twistor theory is, in general, it relates objects of interest in mathematical physics and differential geometry to complex geometry on another space. So we will need some language and basic ideas from complex geometry. So in that direction, let's just recall to begin with that if we take the Riemann sphere, the simplest compact complex manifold, just complex numbers with a point at infinity added, then we can study line bundles, holomorphic line bundles over this Riemann sphere, and the basic fact is that those are just given by the degree, an integer d, the powers of the Hopf line bundle. And the notation we want to use is O of D for the line bundle, which is the dth power of the Hopf line bundle. So to describe something about this Twistor theory, we want to consider a three-dimensional complex manifold, Z, which contains what we'll call a line, that's to say an embedded copy of the Riemann sphere, holomorphically embedded copy of the Riemann sphere. And we want to suppose that the normal bundle, N, of this line is isomorphic to the O1 plus O1, that's to say the sum of two copies of the Hopf line bundle. So of course, remember, so Z is three-dimensional, L, the line, is one-dimensional, so the normal bundle, of course, is two-dimensional. So there's a theory going back to Kodara of deforming submanifolds of a complex manifold, and this tells us that our L will move in a family of lines, call it script M, whose tangent space at the given point L is isomorphic to H0 of N. So at the bottom, recall that H0 of N just denotes the holomorphic section of our holomorphic bundle N over L. So in this case, you recall that we take the sections of the Hopf line bundle O of 1, they're just two-dimensional. So the sections of N are dimension 2 plus 2 is 4. So this family of lines is a four-dimensional complex manifold. So a simple but surprising thing is that there is an intrinsic holomorphic conformal structure on this family of lines, M. This comes about in a very simple way. If we write slightly more invariantly, N is S minus tensor O of 1, so S minus is a two-dimensional vector space, then the space of sections is the tensor product of S minus with the sections of O of 1. So let's write S plus for the sections of O of 1. So the tangent bundle is a tensor product, S plus tensor S minus, of a pair of two-dimensional vector spaces. So the observation then is that if we have a tensor product of two-dimensional vector spaces, that automatically has a natural quadratic form defined up to a factor. This is just because if we take we have a skew symmetric map from S plus times S plus to lambda 2 of S plus, similarly for S minus. And if we take the tensor product of those, then we get a symmetric map from Tm tensor Tm to a tensor product of a pair of lines. So trivializing that tensor product, we get, we can think of that as C, we get a quadratic form defined up to a factor. So this is the sort of simple but remarkable thing that if we have a three-dimensional complex manifold containing a family of lines of a suitable sort, then on that family there's an intrinsic conformal structure. Now this picture here is supposed to illustrate some of that. This is Z. We have lines there. Each line Lx corresponds to a point X in our four-dimensional complex manifold M. A more geometric way of expressing what we just said is that if we take infinitesimally, if we look at infinitesimal variations of X, the null variations with respect to our quadratic form just correspond to the variations of our line into a line which intersects Lx. So we take two generic lines in our three-dimensional manifold, won't intersect. There'll be a codimension one set where they do, and if we take the tangent cone of that at x, that gives the null cone of our quadratic form. So the part of this Twistor theory which is most relevant here is what's called the Ward correspondence. I think that they put at the, yes, that's at the heading for this section. This goes back to Ward in the mid-70s, who observed that one could encode the instanton equations, at least initially a complex version of those, in this Twistor geometry. So if we have a holomorphic vector bundle on our complex manifold Z, which is, it happens to be trivial on all the lines in the family M. Then we get a bundle, it's called E tilde over M, that's taking the fiber of E tilde at a point corresponding to a line L, is just the space of holomorphic sections of E over restricted to L. So this is a very simple construction of going from a bundle over Z to a bundle over the family of lines M to M. So there's a way to define a connection on E tilde in this complex geometry framework. A good way of discussing that is in terms of formal neighborhoods. If you have a section of E over L, then you find that there's a unique way of extending that to the first formal neighborhood of L. And that goes over to the notion of a connection. There's an infinitesimal trivialization of the bundle. And then this is a holomorphic anti-self-dual connection over M with respect to the conformal structure that we defined. And conversely, any such anti-self-dual connection comes from a holomorphic bundle. So here we're talking, everything is complex geometry, because that's in a way easier. So we're using the rather obvious extension of everything we did in the real world, four-dimensional world, to the case of complex manifolds. Let's just note, to make maybe help it's clearer, that this condition of being trivial on a line is an open condition. So if we have any holomorphic bundle over Z, provided it's trivial on some line, it's trivial on a whole open set of lines, so to which we could apply the discussion. But for our problem, we want to get to real four manifolds and compact structure groups. And that can be encoded in this Twistor theory by introducing what's called a real structure on Z. In fact, there are different ways of doing that. The most obvious thing to do would be to take, let's just say it this way. There are different ways of doing that which would correspond to different signatures of the quadratic form on the real form manifold. But the one that's relevant to Riemannian geometry is to consider an anti-holomorphic map, sigma, from Z to Z, with no fixed points. Then, although there are no fixed points, we can look at fixed lines, sigma invariant lines. So on each such line, sigma will just be the antipodal map on the two-sphere, which is anti-holomorphic and has no fixed points. Then our complex conformal structure restricts to the four-dimensional manifold, four-real-dimensional manifold of sigma invariant lines to give a positive definite conformal structure. Then the Ward correspondence identifies the anti-self-dual instantons on E with, it's called the real holomorphic bundles. That's to say bundles which, when we pull back by sigma, we take sigma star of E, and take the conjugate dual, that's isomorphic to the bundle E. So all of this was quite general. It applies to quite a number of four manifolds, which can be described in this way. In fact, they're what are called self-dual four manifolds. A particular condition on the Riemannian curvature tensor. But for our problem, we're interested in the four sphere. And for that, we take our complex manifold, is a very familiar one, is just the three-dimensional complex projective space, CP3. So to get the real structure that's relevant to this, we think of the underlying four-dimensional complex vector space as being two copies of the quaternions, H2. So CP3 is the quotient of H2 minus the origin by multiplication by C star. And we get our anti-holomorphic map is just multiplication by J. If our complex structure corresponds to the quaternion I, we take multiplication by J, anti-commutes with I, and gives our anti-holomorphic map. So in that case, our real form, MR, is the four sphere, and the position can be described rather simply from the fact that we can also take the quotient of H2 minus 0 by multiplication by non-zero quaternions, and that will give us the one-dimensional quaternionic projective space, which is just the four sphere. So the real lines are just the fibers of the natural map from CP3 down to S4. And these are lines in the ordinary sense. They're complex line, projective lines in our complex projective free space. And the instantons we seek correspond to certain holomorphic vector bundles over CP3, which satisfy the reality condition with respect to this anti-holomorphic map sigma. But going back to what I was started to say a while ago, a more obvious thing to do would be to take sigma to be an anti-holomorphic map given just by complex conjugation. So that will be different because that has fixed points corresponding to RP3 inside CP3. And one can do the whole theory in that setting, but then we will be studying a quadratic form on RP3 of, a quadratic form on a four manifold with signature 2,2. So we would be working with another discussion in indefinite signature. So here's another picture which is supposed to summarize the discussion. This is the four sphere, which is what we're interested in, on a bundle E tilde over the four sphere. We introduce the Twistor space, CP3, which is in fact a fiber bundle fibering over the four sphere. The fibers give this family of lines, the real lines. Each one is preserved by this anti-holomorphic map sigma. And our Ward correspondence gives a correspondence between certain holomorphic bundles over CP3 and the instanton connections on a bundle E tilde over the four sphere that we want to study. So that's, in a way, the technical background to set the scene for the work of Atiyah, Drinfeld, Hitchin, and Manin. From this point of view, we want to know how to construct holomorphic vector bundles over CP3. So again, let's introduce a little bit more notation. If I have a bundle E over any projective space, we can take the tensor product with the line bundle, O of P, and we just use the abbreviated notation E of P for that. Of course, we can always take the tensor product with O minus P to recover E from E of P. So we don't really lose information of going to these twisted bundles. So the key idea goes back to Horrocks, as mentioned in that quote from Atiyah a while ago, and is what's called a monad, a terminology introduced by Horrocks. These could be considered more generally, but for the case at hand, we just want to consider a very particular situation where we take three complex vector spaces, U, V, and W, and let's write underline U, underline V, and underline W for the corresponding trivial vector bundles over, in this case, CP3. So supposing we have bundle maps, holomorphic bundle maps from the twist of U minus 1, we have a map A to the trivial bundle with fiber V, and then we have another map B to the twist W of 1. And let's suppose A is everywhere injective, B is everywhere surjective, and the composite of B with A is 0. Such a thing is called a monad. Then we get a bundle by taking the cohomology. We take the kernel of B and divide by the image of A. Now this is somehow a combination of the two more familiar things, either considering subbundles for trivial bundle or quotient bundles for trivial bundle. Here we're doing a combination of the two. In any case, such a thing is a very, in a sense, explicit object. If we take homogeneous coordinates for our projective space, Zi, so I goes from 1 to 4, then talking about a map from this twist of U to V, that just says A is can be written as the sum of, say, AI Zi, and B is the sum of Bj Zj. The condition that the composite B with A is 0 is just that when we take Bj Ai plus Bi Aj is 0 for all pairs Ij. So these monads just correspond to solutions of a rather explicit set of matrix equations for a collection of matrices, the A's and the B's. So the relevant theorem, where this brings these monads to the fore, is a result of Barth. Well, it's attributed to Barth by Atiyah. In the references I gave, a more detailed proof appeared in a paper of Barth and Hulek in 1978. And it says that if we have any holomorphic bundle over CP3, which satisfies certain vanishing conditions on its cohomology, then such a bundle arises from a monad of the kind we were describing, where the dimension of U and V and W are given by the Chern class and the rank of the bundle E. So these cohomology groups, what called sheaf cohomology groups, the H1s and so on, there are the sort of central, maybe technical notion in this ADHM work. But for those who are not so familiar with those things, let's just imagine that just like if we have a topological space, we have homology groups and cohomology groups where the H0 is just detects the number of components, and then the higher cohomology groups detect more subtle phenomena. So recall that if we have a vector bundle, or say a sheaf of sections, then we can take the global sections, which are the H0s, and then we have higher cohomology groups in general, which detect some more subtle information. So what happens if we put together this monad construction for a bundle with the Ward correspondence? Then it gives exactly the induced connection construction for our connection on a bundle over the force sphere. In fact, we can say this in a purely holomorphic language. We don't need to introduce metrics to discuss this, although in the end, for bundles with real structures, one can do that, as in the way we said before. It's to say, supposing we take a line L over which our bundle E is trivial, then we take a pair of points, P1 and P2, distinct points on the line L. Then if you look at the monad, you can see that the triviality over L can be expressed as a simple transversality condition for the linear maps involved. We have our bundle map, say B1, which we can evaluate at the point P1, well, this is defined sort of up to a scalar, but if we make up a scalar ambiguity won't matter here. And similarly for B2, and similarly for A1 and A2. So we have 4 linear maps between 3 vector spaces, and the triviality condition is that these are in general position, in a sense. So the restriction of E to L can be described either as a subspace of our vector space V, the intersection of the kernels, or as a quotient of V, the quotient by the sum of the images. So those 2 descriptions are just what we need to describe the induced connection in the way that we did. We have an inclusion map of E tilde into a trivial bundle and a projection map from the trivial bundle onto E tilde. So with all that in place, all we have to do is to show that the bundle E, which we have over CP3, according to the Ward correspondence, corresponding to an instanton, satisfies all those vanishing criteria in Barth's theorem. Remember, they had all this stuff about the H0s and the H1s of E and E star. So the essential case, the H0s are rather obvious, in fact, but the essential case is the vanishing of the H1 of E minus 2, and similarly replace E by the dual bundle, E star. So the argument for this is interesting, and it goes back to the sort of the origins of Penrose's Twistor theory, and a sort of earlier part of the story of the development of this Twistor theory. So let's digress to explain that. So this is just a really local discussion initially. If we just take an open set in R4, we can take the corresponding open set in CP3, just the union of all the lines corresponding to our open set in R4. So let's call that script U. So if we have a sheaf cohomology class in H1 of the script U with coefficients in the bundle O minus 2, then we can restrict that to any line in our family. So for a line, the H1 of O minus 2 over a line is just one-dimensional. So we can, in this situation, we can identify it with the complex numbers. So the restriction of this sheaf cohomology class to lines gives a function on U. And Penrose showed that this function satisfies the Laplace equation, the ordinary Laplace equation in R4. And conversely, any local solution of the Laplace equation arises in this way. This is a very attractive idea and related to some sort of classical analysis and things. There are classical representations for harmonic functions in various contexts in terms of contour integration of holomorphic functions. And if we take this Penrose construction, if we represent our H1 class in terms of check cohomology, so we have a holomorphic function of three complex variables defined on an overlap of two domains for suitable kind, then you find that explicitly the corresponding harmonic function would be given by a contour integral of our holomorphic function around a suitable family of contours, a formula of the classical nature. So in the same way, going back to a situation of our bundle E on CP3, corresponding to an instanton connection on tilde E over the force sphere, then this cohomology group of interest, the H1 of E minus 2, can be identified with the space of sections of E tilde which satisfy an equation. The equation is a variant of the Laplace equation, the case we were discussing before. And that variant comes about in two ways. One is that we're considering sections of a bundle. So we take the covariant Laplacian formed using the covariant derivative. And the other is we're working now on the force sphere. So what appears is what's called the conformally invariant Laplacian, where we add on a multiple of the scalar curvature, R over 6, where R is the scalar curvature. This is something which is, when we make a conformal transformation, goes over to the ordinary, the standard Laplacian on R4. But anyway, working globally, since the scalar curvature is positive, the first term, nabla star nabla, is a positive operator. The only solution to this equation is S equals 0. So we find that H1 of E minus 2 is 0 as desired. The same applies to E star. And we can apply Barth's theorem. So all we need to do, looking at the time, all we need to do to understand this ADHM result, if you grant the various assertions that I've quoted, is to understand how to prove Barth's theorem. Why do all the bundles satisfying certain vanishing theorems come from this rather simple monad construction? So the quickest, slickest proof of that nowadays comes from using a construction of Donaldson, which appeared somewhat after the ADHM work, probably very likely motivated by the ADHM work. And I think that develops ideas of Drinfeld and Manin. So let me try to give some idea of this Donaldson construction. In fact, the Bailyn construction applies initially for bundles over any projective space, though we're going to apply it for the specific case to a bundle over CP3. So let's, to begin with, let's fix a point X in a projective space, CPN. Then there's a preferred section of, let's call it V, of the tangent bundle twisted by -1, which has a simple 0 at X and no other zeros. So this is essentially a very familiar thing. If we took affine coordinates, so we took Cn sitting inside Cpn, then this V would appear as an ordinary vector field, and it's just the radial vector field, the sum of Zi d by dzi, the field generated which generates radial dilations. So the effect of twisting by -1 when you go to the projective space is to make it non-vanishing at the hyperplane at infinity. The next, recall a very basic, simple thing. If we have a vector space, call it K, a non-zero vector E, then we get an exact sequence which we start off mapping, on the right, we start off mapping K star to C, just the pairing with E, and then we put all the exterior powers of K star, and we map from one to the other by using contraction with E. And the basic fact that this sequence is exact, provided E is non-zero. Of course, if E is 0, all the maps vanish. So I can apply this idea in the setting of bundles and sheaves to give what's called a causal complex, which in our situation is an exact sequence of sheaves where we take the omega r twisted by r. So omega r is just notation for the exterior power of the cotangent bundle, the dual of the tangent bundle. And then essentially contraction with our section defines maps from omega r twisted by r to omega r minus 1 twisted by r minus 1, and so on. At the end, we go from omega 1 twisted by 1 down to the functions, but because our v vanishes at 0, that's not surjective. A function lies in the image of that map, if and only if it vanishes at the origin. So we put on the skyscraper sheaf at x, the sheaf given by a copy of C, so concentrated at x, at the end of the sequence. So now if we have a holomorphic vector bundle, E, over our projective space, we can take the tensor product with E, with everything we did above, and then we get an exact sequence of sheaves. So we'll write these as script F for shorthand, but ending up with the fiber of E over X. So in this general situation, if we have an exact sequence of sheaves, then one has what's called a hypercohomology spectral sequence. In fact, we have a pair of spectral sequences which abut to the same limit. So, but in the case at hand, one of those sequences is trivial, and so what we get is a spectral sequence which begins with the cohomology of all our sheaves and abuts to the fiber of E at X, just that vector space. So again, for people who are not so familiar with sheaves and so on, spectral sequences and so on, what this means is that we have, starting with E, we make a collection of other bundles given by taking tensor product with these standard bundles we have in projective space built out of the tangent bundle. Then we go, so we have all those bundles, we take all their cohomology groups, so we get a big chessboard of cohomology groups, but then we have lots of maps induced by our section between those, and then there are more subtle maps between the kernels of the first lot of maps and the images and so forth. So we get a whole principal big collection of linear algebra data, but in the end, that gives some way of describing the fiber of E over X. So that's the general story. Let's look at our case. Our spectral sequence begins with this chessboard of vector spaces, the cohomology HQ of E tensor these twisted exterior powers of the cotangent bundles. N is 3. So in fact, we're going to, it's convenient to replace E by the twist, E minus 2. So then what you find is that the rows of our chessboard have got the cohomology HQ of E minus 3, and then E tensor omega 2, the second exterior power of the cotangent bundle, and E tensor omega 1 minus 1, and then we get E minus 2 appearing here. So here we can see that the E minus 2, remember that was just the crucial thing for the H1 of E minus 2, That's just the crucial thing appearing in Barth's theorem. That's when Q is 1. We also have Q equals 2, but then that the H2 of E minus 2 is ser dual to the H1 of E star minus 2. So that also vanishes. So putting together that and various standard arguments, you find that out of this big potential chessboard of cohomology spaces, a very complicated description, actually things become very simple. There are only 3 terms in the E1 term of our E1 page of our spectral sequence, and the spectral sequence just amounts to the statement that the fiber of E, or in fact E minus 2 at our point X, is given by the kernel of a map B for one space divided by the image of another map A. In other words, just the kind of thing that we are looking for from our monad. And indeed, if we now let the point X vary on CP3, then we have to keep track of the scalar ambiguity in the section V, and also the fact that we made this twist from E to E of minus 2. But when you keep track of all that, what you find is that the bundle E is described as the cohomology of a monad of the kind we want, where the vector space U is the H2 of E minus 3, V is the H2 of E tensor omega 2, and W is the H2 of E tensor omega 1 twisted by minus 1. So this Bailenson construction makes this result about monads appear as part of a larger picture. For any bundle whatsoever, you get some kind of potentially complicated description of the bundle in terms of linear algebra built out of its cohomology groups. But this can be, in the general situation, as done by Bailenson, one should really talk about the derived category of sheaves, and his theory gives information about that. So another way of saying the last part, when we let X vary, is that we should really work not on CP3, but on the product CPT times CP3, and then rather than working with a resolution of the ideal sheaf of a point, we should work with the resolution of the diagonal in CP3 times CP3, and that does everything in sort of in one blow, but with a more complicated notation. So that, we've just gone for about an hour, that completes the main part of the talk, giving an account of the ADHM work, more or less in the way they did it, with this refinement from Bailenson. Now we go on to the last section of the talk, where I'm going to talk about some other points of view and further directions. And one of these goes back to Mukai, published in 1981, so more or less at the same time. But this was from a completely different direction. Mukai was, I think, had no knowledge or interest in instantons at that time, as far as I know. He was studying holomorphic bundles, or more generally sheaves, over a complex torus. Well, again, his theory applies largely to any dimension, but in the case at hand, we want to take a two-dimensional complex torus, two complex dimension. So in that situation, we have a dual torus, T hat, which parameterizes the flat line bundles over T. So for any point psi and T hat, we have a flat line bundle L psi over T. So if we start with the holomorphic bundle E over T, then in favorable circumstances, we get a bundle E hat over T hat. So the fiber of E hat at the point psi is given by taking the H1 over T of E twisted by the line bundle L psi. So here, a bit more precise, the favorable circumstances mean a situation where we know that the other cohomology groups, the H0 and the H2, both vanish. Then Mukai showed that this had a striking property closely analogous to the Fourier transform, that if we take the dual of the torus, we get back to original torus. So we can start with E hat and do the same construction, and then we recover the bundle E up to a sign. We might have to take the involution of the torus. Well, we do have to take the involution of the torus mapping x to minus x. Just as in the usual Fourier inversion formula, you need to put in a change of sign. So there are quite precise analogies between the Mukai construction and the Fourier transform. So that was a complex geometry discussion in terms of cohomology. But we can also make a Riemannian geometry discussion, which turns out to be equivalent for rather simple reasons. If we take a flat metric on T, compatible with a complex structure, then we can describe the same bundle E hat using the Dirac operator. So we take the Dirac operator mapping coupled negative spinors to positive spinors, but all twisted with this line bundle L psi. And the kernel of that, by well-known standard results, can be identified with the H1 in the previous setting. So this description is independent of the complex structure. And using a natural projection construction, similar to what we said before, if we start with an instant connection on the bundle E, we get an induced instanton connection on E hat. So while Mukai's work was in the setting of complex geometry, there's a translation of that into the setting of instanton geometry. There's speaking of Fourier transform that takes instantons on one torus to instantons on another torus. But in a sense, this interchanges essentially the two topological invariants, the rank and the Chern class. So it's a not at all an obvious construction. So developing that line of ideas, let's go back to the instanton equation on R4 and think about that. So we can write that equation in terms of the covariance, the components of the covariant derivative as, remember the curvature is given by the commutators of these components. So we've expressed the anti-self duality condition in terms of commutators in this way. So if a convenient way is to take coordinates on R4 going from 0 to 3, we take the following expression. We take the commutator of grad 0 with grad I and add commutator of grad j and grad k, and then ijk run over the cyclic permutations of 1, 2, 3. So now let's take complex combinations. Let's write d1 is grad 0 plus I times grad 1, square root of minus 1 times grad 1, and similarly for d2. Then instanton equations can be written in terms of the d's as saying that d1 and d2 commute, and then we take the bracket of d1 and d1 star, and d2 and d2 star, those sum to 0. So in fact, the fact that we get this commutator equation, d1 bracket d2 is 0, essentially is another point of view on the connection to holomorphic structures. If we fix complex coordinates corresponding to the way we've done things, so we take one complex coordinate to be x0 plus ix1, the other to be x2 plus ix3, then D1 and D2 correspond to the Cauchy-Riemann operators in the two complex coordinate directions. And this commutating condition is just the integrability condition that the connection defines a holomorphic structure. On the other hand, here we fixed this particular Kaisel complex structure. We could have taken any complex structure compatible with our metric on R4, and so we get a whole family of similar integrability conditions. And essentially that goes back to the point of view of the holomorphic bundle on CP3. There are also connections with, important connections with integrable systems, where one would talk about the lax representation of a, if I write a nonlinear equation, express it in lax form as the commutator of two related linear operators. And there's a big literature relating these instanton equations to integrable systems, such as the KdV equations. So one of the pioneering papers was Mason and Sparling in that direction. In any case, looking at these equations, the D1 bracket D2 is 0, and then we have the other equation involving the stars. And the matrix equations arising from the ADHM construction can be put in a similar shape. Remember, we omitted to say exactly what the equations came down to, but now we're going to make up for that. So you can put the equations in the following form. Your data consists of a pair of linear maps from CK to CK, call it alpha 1 and alpha 2, a map from P from CR to CK, and Q from CK to CR. So there's 4 different complex matrices is our data. And then the equations, which all this monad theory lead to, can be expressed in the following way, that the bracket of alpha 1 and alpha 2 is P times composed with Q, and the sum of these other terms is PP star minus Q star Q. So if we were just able to set P and Q to 0, ignore the right-hand side, we would have exactly the same structure as the equations for the differential operators that we were considering before. But just to complete the story, the ADHM description of the connection involved this family of maps lambda x, written the following way, and I've just written down here how explicitly to write out these lambda x in terms of the data that we're looking at now, the alphas and the p's and the q's. So working in R4, the vector space U that we said, that in the complex geometry description, that appears as an H2, also as an H1. But in R4, it appears as the space of solutions of the coupled Dirac equation. And one can write down, in fact, just directly write down a formula for all the ADHM data. I have this vector space. We have to find ways of writing down these linear maps and directly confirm the ADHM result just by differential geometric calculations on R4. And this was done first by Corrigan and Gard in the early 80s. So another development from the same time, this important development and work of Fourier-Nahm of the early 80s. So this takes, we look at what's interesting in what are called monopoles, which are the solutions of the instanton equations which are invariant under translations in one direction. So they can be expressed in terms of the solutions of some equations over R3. And one studies those with suitable asymptotic conditions at infinity. And Nahm showed that there was a transform in the same vein as the Mukai transform, or also as the ADHM construction, which took these R invariant solutions of the instanton equations to R3 invariant solutions, solutions of the equations which are invariant under 3 translations. So for these latter, the partial differential equations just come down to ordinary differential equations, and one is just studying solutions of Nahm's equations, which are these system of ODEs for matrix valued functions of one variable S. So the general picture is that in many contexts, one gets a transform which takes one version of the instanton equation to another one. So we might call this the ADHM Fourier-Nahm transform that arises in many contexts. In the ADHM case, we have the P and Q, so it's a bit more subtle. Roughly, if you did an approximate calculation on R4, you would get the equations without the P and Q, but when you think the P and Q arise because there are certain contribution from boundary conditions, the boundary terms at infinity in your calculation. So that's where the terms corresponding to P and Q arise. But the general picture is that one has, say, a transform in these different settings from one version of the instanton equation to another one. And this is a useful survey of that is given by Marcos Jardim, the reference quoted. Coming then towards the end of the talk, what we have these UR instantons on S4 for each Chern class, which is a positive number, K. So we have a family of these moduli spaces, MKR, which grow in dimension. The dimension is something like 4KR, something like that. So let's give 2 out of many examples of application of this ADHM theory involving these moduli spaces in different ways. One is in the direction of topology. It's work of Boyer, Hertubis, Milgram, Mann, and then also of Kerwin, related work. So these give, roughly speaking, calculations of the homology groups of these moduli spaces in a stable range where the K is very large compared to the dimension of the homology group you're interested in, the rank of the homology group you're interested in. Actually, maybe it'd be more precise to say, rather than calculation, but they show that these homology groups are isomorphic to homology groups of another space, which is well known in algebraic topology, the third loop space of the corresponding group. So this was the confirmation of called the Atiyah-Jones conjecture, which was an influential problem in the 80s and early 90s. In another direction, more directly related to physics, Nekrasov, 2003, used the ADHM description of the moduli spaces to find what's called the Seiberg-Witten prepotential, which I believe is an important thing in supersymmetric quantum field theory, by expressing this in terms of integration over the moduli spaces and then using localization techniques to evaluate the integrals. So there are many other applications, both related to geometry, topology, and others to physics, of this explicit description of, say, relatively explicit description of the instanton moduli spaces. Finally, we could mention some current and possibly future directions of research which are, involve many of the same ideas that we've touched on here. In one, again, there'd be many things that one could say here. I'm just choosing 2. In one direction, there's increasing interest recently in looking at instanton equations and variants of those equations for non-compact groups, such as SL2 of C, for example. So this comes from work of, for example, through work of Taubes and others in the last few years. as we said, the basic Ward correspondence applies just as well for non-compact structure groups. So one can describe these instantons in terms of algebraic geometry of bundles on CP3, although at least in principle. And one could ask whether if you take a general formula fold, one would reproduce the same kind of phenomena that one can find through algebraic geometry in the special case of the fourth sphere. Another direction is that the study of holomorphic bundles on projective space for various dimensions, but dimensions 2, 3, and 4, is important in different ways in the theory of some certain higher dimensional versions of the instanton equation, which are being actively pursued nowadays, which occur in the context of manifolds with exceptional holonomy or special holonomy. So again, there's a lot of scope for work in that direction in the next few years, I think. So thank you for your attention. That finishes my presentation.
Great, thank you very much, Simon. Let's have some questions.
So there are 4 questions in Q&A section.
Okay, so if I stop the share. How do I get to the questions? I see, okay, right. Okay, so so the first question was Manin's contribution joint with Drinfeld, or was Drinfeld independent? I understand that Drinfeld and Manin were working together at that time. Okay, another question I see also from Jim Staffish. Yes, I apologize, there's a misspelling. Hurtubise has an R, which I misspelled. Jacques Hurtubise has an R. So there's another question, so I apologize, I didn't see this as we were going through. To say that sigma has no fixed points, there's no point in our, so in this case, in the case at hand in CP3, which was fixed by sigma. So this, so the model will be to think of the antipodal map on the 2-sphere. There's no point which is preserved by the antipodal map. I see another question from Sergei Cherkis. Why is it called a monad? I'm not quite sure. I did look at the paper of Horrocks. I didn't find any explanation of why he chose that name. And I think a monad means a sort of a fundamental entity in some way. So perhaps that was the idea he had. Okay, so I see a question from Conan Young. How are bundles over CP3 and CP4 related to special holonomy? Okay, so in fact, another point of view on what we would on this instanton story would be to say that bundles over instantons on R4 in fact correspond to holomorphic bundles on CP2, which are trivial on the line at infinity. That this is something that's related to the Twistor story and also other things. In the same way, if you look at, say, what are called Hermitian-Yang-Mills equations on C3, which are, have certain decay properties at infinity, then those can be identified with certain holomorphic bundles over CP3, and similarly for CP4. So those Hermitian-Yang-Mills solutions give models for solutions of these various higher dimensional instanton equations one would have over manifolds of dimension 6, 7, and 8, roughly speaking. That's one answer to the question.
So are there more questions?
Oh, I see a question about the connection to interval system via Lax pair. So the question is, with this connection to interval systems, does a spectral curve arise which gave data about the instanton? So I'd have to think about that in the case we were discussing for the main part of the talk, but in the variant in the case of Nahm's equations, then the answer is definitely yes. As studied in many papers of Nigel Hitchin, there is these monopoles on R3 can be, in fact, described in terms of a spectral curve, which one can see either through Nahm's equations, essentially the joint built out of the eigenvalues of the family of matrices Ti, we wrote down, or can be described directly in terms of the geometry on R3 of the monopole.
So any more questions?
Looks like someone has their hand raised.
Yeah.
Jim Eisberg. I'll allow him to talk.
So are there more questions? So yes, so there's a question. So there's a question from Marco Grazieri about asking to comment about how learning about the instantons on R4 led into to use these moduli spaces to study formula folds. So I think that the answer to that is that, at least in my case, it's natural just within this Yang-Mills setting to study compactifications of these moduli spaces. And that sort of corresponds to the analysis questions about the behavior of sequences of instantons, what I can say about. Once one starts that, then you find was applications to formula folds, well, sort of sitting in your hands. I said I never had a plan to sit down and say I'm going to study formula folds using moduli spaces. You see that the existence of these moduli spaces will give you some information about the topology of the formula folds that you're working with.
Any more questions?
Yes, can you hear me? Can you hear me? Yes. So I had a question. So way back in the late 70s, there was some simultaneous work by Ed Whitten and also by me and Yaskin and Green, where we looked at a version of, instead of looking at bundles over CP3, we looked at bundles over what we called ambitwistor space. And what we got was a correspondence of these bundles with Yang-Mills solutions rather than self-dual Yang-Mills solutions. The problem with that construction is that nobody ever knew anything about those bundles. I'm just curious if you've ever looked at that work from, as I said, Whitten did it in around 79, and I also did with Phil Yaskin and Paul Green. Are you familiar with that work at all?
Yeah, I'm sorry that the sound is very unclear, so I couldn't really get much of your.
So this is work of looking at a correspondence of full Yang-Mills solutions over on Minkowski space or complex Minkowski space with bundles over what we call image twistor space, which is sort of a diagonal of CP3 over CP3. Can you hear me?
So I think so. We're discussing the ideas of extending this description of the instantons to description of solutions of the full second order Yang-Mills equation.
Yes, that's right, Joe. There was a paper by Ed Witten and also a separate paper by me and Yaskin at Green.
That's right. There was some activity in that direction, but it's not an area I've really followed. It would be interesting perhaps to go back to that because some years after that, people proved by other means the existence of global solutions to these second order equations.
Yes.
It would be interesting to see whether those could be found using this geometrical construction. But it's not something I've ever really looked into myself much.
Okay, thank you.
Okay, are there any other questions? Okay, we should thank Simon for this beautiful talk, really nice and inspiring. And we should clap our hands. Tomorrow there will be 2 talks, one on black hole, one on quantum groups. The black hole will start at 11 by Lydia Berlier, and quantum groups will be by Pavel Ettinger. So I hope to see you tomorrow. Thank you very much, Simon.
Sure, a pleasure. Thank you very much.
Yeah, beautiful talk.
Right. Okay. Right.
Okay, see you guys.
Right. Bye.
Bye.